This video is part 2 for this other video that I made earlier about hypothesis testing. So if you've never heard of hypothesis testing before, you should definitely watch the other one first because I explained it there and I am not going to explain it again in this video. Other than that, it's probably fine if you watch whichever one first, but it might still make a little bit more sense to start with the other one because over there I was talking about things that you can do for one variable of data, and this video is going to be about things that you can do with bivariate data. These are very useful things that an IB student can probably make good use of in the IAs that they're writing. Even if we're talking about students that are taking the AA math course, which does not have these things in the syllabus, but the AI course does, at least in the high level. So today we're going to do things with a bivariate data set, and I've started with 20 points that are randomly generated. I asked Google Sheets to give me random points because usually when you have a bivariate data set, the main thing that you want to do is test if there is any kind of correlation between the two variables. So I thought we'd start with random points, which clearly we know that can't be correlated because every number in this set is random. But let's pretend that these numbers are coming from something that you investigated, some data that you collected, where you don't actually know that they're not correlated, but it might be the case. So that's exactly what we're trying to decide. The first thing that you're going to do, obviously, is to do the scatter plot. As these are randomly generated numbers, the scatter plot looks very random, but you still should go look for the line of best fit and the Pearson's correlation coefficient. So let me do that in Google Sheets. You click the graph and then you try to edit it. Then you click here in Customize, go to Series, and scroll down a little bit to find this box that says Trend Line. You see the line of best fit is already in the graph now. It looks like a little bit of a negative correlation. And two other things that I really want to do in this screen. First, click this box that says Show R squared. R squared is the coefficient of determination. It's not Pearson's correlation coefficient. That is just R, but this is the square of that. So if you want to find Pearson's from this number, just take the square root. And the other thing here in the label is that I want to tell it to use equation, because then I already have the equation of my line of best fit. Now, you might be wondering why I would do these things in Google Sheets instead of just using my TI-84 that I really love. But the thing is that this example only has 20 points, which is already a little bit boring to type in the calculator, but later I am going to try to do this with a lot more points, and I definitely wouldn't want to have to type them individually in the calculator. Hopefully, for any practical application that you're doing, like an IA, you are also going to have this problem of having too many numbers that you don't want to type in the TI-84. So that's why I'm showing you how to do it in Google Sheets, but I'm going to do it in the TI as well. So now we have an example where Google Sheets is telling us that the R squared is 0.16. Taking the square root of that, I find that the Pearson's coefficient is negative 0.4. And I chose the negative sign, obviously, because I can see that the line of best fit is going down. It has a negative slope. Pearson's correlation coefficient is not the slope of the line of best fit, but they do have the same sign. So if you remember the first time that you were introduced to this Pearson's correlation coefficient, it is a number that goes from negative 1 to 1. And if it is equal to 0, that means no correlation at all. And then if it's negative 1 or 1, it means a perfect correlation, either negative or positive. And anything in between is different strengths of correlation. Negative 0.4 is a pretty ambiguous number. If it was like 0.9, it would be a very strong correlation. 0.8, I would still consider strong. But 0.4, is it a very weak correlation? Is it no correlation at all? It's weird to say that it's no correlation at all, because 0.4 is almost 0.5, and 0.5 is half. It feels like it should be half correlated, like sort of correlated, and yet we know that these are random numbers. it may be, as it is in this case, that you are not seeing exactly zero correlation, because that would also be very unlikely to have a perfect zero, even with randomly generated numbers. 0.4 may be kind of a stretch. It's a little too big for no correlation. So you might be wondering, how many times did I have to try this in Google Sheets until I found a set of numbers that looked weird for random numbers? And the answer is 2. I did discard the first set of numbers that he gave me because the correlation was way too small and it wouldn't be interesting. But after that, I can try to do this many times again and see what usually happens with 20 randomly generated points. So let's change the numbers and watch what happens to the R square in the picture. This one is 0.113. It's smaller than the previous one, but not that small. Here we have one that is very small, very, very small. See, most of them are really small. I found a big one again. It happens every once in a while. One of the things that we are going to calculate is how often do we expect these things to happen, these weirdly big numbers for correlation of random numbers. Anyway, back to the data set that we're actually going to study. I did already type it in the TI-84 here in stat edit. These are the same numbers. And to do the same thing that we just did in Google Sheets, stat, calc, linreg, x list is L1, the y list is L2. I am not using frac list in this example, so clear that and calculate. There you go, the same numbers that Google Sheets gave us. They are slightly different because I am seeing more significant figures, and also because I typed the numbers only with 2 decimal places. Okay, so Google Sheets is working with more significant figures than I am. Every result that we compare are going to be a little bit different from each other just due to these approximations. But there is something else slightly different that you can also do in the TI, which is this. Stat. Now, instead of going to calc to do your linreg, you go to tests instead. Let's do a hypothesis test on this result. Like I mentioned in the other video, all kinds of hypothesis tests have some of the same elements, like the null hypothesis and the alternative hypothesis. In the other video, we studied the chi-squared goodness of fit test and some t-tests that were trying to test something different than this one. This is the t-test for linear correlation. So the null hypothesis that you're going to use in this case is always this. Rho is equal to 0. Rho is a Greek letter. It has a strange name. But what it means is the Pearson's correlation coefficient, okay? Exactly the same thing that you're used to calling R. And the null hypothesis is that it's 0 because that's what null means. That's nothing happening, so 0 correlation. And as for the alternative hypothesis, you get to choose which one of these 3 you want, depending on your context. And again, this is very similar to what happened in the other video for the other t-test that we did. For my purposes today, I think that the most adequate one is this. It is a two-sided test or a two-tailed test because I'm basically asking random or not random. I am not interested in one variable influencing the other in a particular way because they are just random numbers. But in your context, if you suspect that one variable might have a positive influence on the other one, then you could choose this, for example, or this one if you suspect a negative influence. That's all depending on context, and then you explain what you're doing and why. 2 other elements that all hypothesis tests have. One is the significance level, which we are going to keep using 0.05 like we did in the other video for the other tests. And the other one is the degrees of freedom. In this case, the degrees of freedom are calculated by subtracting 2 from the number of pairs of points that we have. So in my first example, I have 20 pairs, and my degrees of freedom will be 18. And the final element for the hypothesis test is going to be the calculated P, the probability of observing data that is as weird as yours in case the null hypothesis is true. That is the same for all kinds of hypothesis testing. That is the basic structure of how this always works. We have a null hypothesis, basically nothing is happening. We calculate a probability of observing your data if that's true. And then if the probability is small, so that's an unlikely thing to happen, we consider that the null hypothesis is rejected because that would be too unlikely. Rejecting H0 is more evidence towards H1, but the correct way to say it is reject H0. It's not accept H1. And the way we decide whether the probability of finding these values is too small is to compare it with another number, which is exactly what the significance level is for. We are going to use the calculator, use the technology to find the value of this probability, and then we're going to compare it with 0.05. If it's smaller, then that means we reject the null hypothesis. You scroll down almost to the bottom of the list, okay? The one that you want is the Linreg t-test. And you don't have to do the other one before you do this one, okay? You can just go straight here. It's very similar. The X list is L1, the Y list is L2. I'm not using frequency list. The null hypothesis is always that the Pearson's coefficient is 0, but my alternative hypothesis that I want is that it's different from 0, because if random numbers are going to show me a fake correlation, it's just as likely to be positive or negative. And then you calculate, and a lot of the stuff that you see here, you had already seen in the other screen as well. That's why you don't even need to do the other one first. So a few things are new. We are seeing a T number that is negative 1.84. We are seeing a P number, which is 0.0827. And that is the one that we are going to use to resolve the hypothesis test, okay? That's the probability of finding such results under the null hypothesis. We're also seeing df is equal 18. Those are the degrees of freedom. A and B are the coefficients of the line of best fit, same numbers as we got before. I don't know what this S is, but R squared is the coefficient of determination, and R is Pearson's correlation coefficient. Right, so now I want to show you how to do the same thing in Google Sheets, and I am disappointed by this process. I wish there was just a button that I could click and select the numbers and it would give me the answer, like what happened in the TI-84. But it is going to be the mystical use of a formula, which is really not something that I like. I like to use formulas and do things by hand when I know what I'm doing, not when I'm just applying a formula. I might as well click a button and ask the computer to do it for me. Anyway, I don't know that Google Sheets has an option to do that. So here's what you're going to do. So first you're going to type the command Pearson. He wants data Y first and data X next. Not that it would change the Pearson coefficient, but the data Y is the interval here from B1 to B20. And the data X is the A column from A1 to A20. That's the Pearson coefficient, now with more significant figures than we had seen before from the graph. And it's a little bit different than the one that the TI gave me, like I said, because of the number of significant figures that I typed there isn't the same as the ones that Google Sheet has. I'm only showing 2 here, but you see that it has more. Right, so now that we have Pearson's coefficient in cell C1, all that we are going to do is to type this very disappointing formula where we multiply it by the square root of the degrees of freedom, and then we're going to divide that by the square root of 1 minus the Pearson's correlation coefficient squared. I know this is terrible, it's just a formula. But now that we have the result of that formula here in cell C2, what we are going to do with it is to use it as the parameter for a t-distribution. This is why this is called a t-test, by the way. There is such a thing as a t-distribution. It's a different distribution that we don't really study in the syllabus of the IB courses. Yeah, it's a continuous distribution, which is not the normal distribution. So this would be something like the normal CDF as an analogy, where we are going to ask the t distribution what is the probability of being away from the center, like from the expected value. How far away? Well, the number that we've just calculated, which is in cell C2. Again, it wants the degrees of freedom. Remember, it was 18. Now, as for tails, it's just one or two here in the Google Sheets command, whether we're trying to go to one side or two sides. So let's agree to go to both sides because we are interested in the alternative hypothesis, the Pearson's coefficient being not equal to zero, okay? Either less than zero or more than zero, doesn't matter. So that's two tails, left and right. Ah, an error. He doesn't want a negative number. And C2 is a negative number. Well, that's easy to fix. Let's put a minus here. 0.0802, and that should be compared with the p-value that we found from the calculator before, which was 0.0827. Again, a small difference due to the significant figures and approximations. So in this case, as we have found the p of 0.0827, that is actually bigger than alpha 0.05, so we do not reject age 0. Do not reject the null hypothesis. Again, be careful not to say that you accept the null hypothesis, because accepting the null hypothesis means that you're saying that for sure they are uncorrelated. And that is not the same thing. Not rejecting it means that you still consider the possibility that they might actually be uncorrelated. So let's remember what this number means. It means that if the variables are uncorrelated, the Pearson's coefficient is 0, then there is an 8.27% chance of finding such numbers as we did. That sounds really small, but it's really like 1 in 12 approximately. So that should explain why it didn't take me that long to find numbers that looked weird, because I only expected to have to try 12 times. Okay, so how happy are you with your data at this point? Probably not very much. You were studying something and you had 20 data points. You wanted to find a correlation, but you didn't. You found 0.4 as a Pearson's coefficient. You even ran a hypothesis test on that to see if, although small, maybe that 0.4 could already be considered something of a correlation, even though a weak correlation. And then the hypothesis test was not on your side. It said, do not reject the null hypothesis that this is just no correlation at all. You do not have the right at this point to claim that it's a weak correlation, because the hypothesis test is telling you not to reject the null hypothesis. But what you wanted was for the data to not be completely random. You were studying something. So you were almost losing hope, but don't lose hope, because 0.08 did not reject the null hypothesis, but it was not a big number either. 0.08 is a small number. So there is still something that you can do. You can ask the next question. Okay, so my data is not correlated, or I can't claim a correlation, but is it at least dependent? Like, okay, so I can't claim a particular type of correlation between these two variables that I'm studying, but are they really just independent variables? I don't think so. So the next test that we're going to do is going to be about independence, not correlation. And it's important for you to understand that two variables not being independent is a weaker statement than them being correlated. In other words, correlation is stronger than dependence, because correlation says a particular way in which one influences the other. It's not just, oh, they're not independent. The bottom line is, it doesn't make sense to run the following test, what we're going to do now, if you found a strong correlation. It's something that you do as a plan B. It's something that you do if your correlation did not work. Of course, if you do run the independence test, you are going to find out that they are not independent. But that, at that point, is not adding any new information. You already knew that they were not independent. They were correlated. What I'm telling you now is what to do in the awkward case, where you're still not sure if there is anything between these two variables or not. So here's yet another type of hypothesis test that I want to show you. And I shouldn't repeat something that I said in the other video, that for each type of hypothesis test, what the null and alternative hypotheses are is predetermined, okay? You have to know what to write for these hypotheses if you know this kind of test. So for the chi-square test for independence, the null hypothesis is that the variables are independent. You don't get a choice in that. Sometimes you get a little bit of a choice, like in the t-test we were talking about before. You get to choose if the h1 is bigger than 0 or less than 0, but you don't have more freedom than that to choose your hypothesis. So chi-square test for independence, h0 the variables are independent, h1 they are not independent. Significance level, we are going to keep using the 0.05, and the degrees of freedom are going to depend on the structure of how we are categorizing our pairs of numbers according to one variable and according to the other variable. So in this example, I am categorizing one of the variables in 3 different categories and the other variable in 2 different categories. So if we call this number n and that number m, then the degrees of freedom are calculated by n minus 1 times m minus 1, which in this example here would be 2, but that's not the example that I'm going to use in my data set. The smallest table that you can make is a 2 by 2 table, and in that case the number of degrees of freedom is 1, because it can't be any less than 1. So that is the smallest structure that you can make, probably what I want in my example, because I don't have a lot of points. And something that is interesting to mention here is that unlike some other hypothesis tests that we've seen before, this one doesn't need to work with numerical data. Categories can be something like blue and red, small and big, because you're testing for independence of 2 variables that has to do with the probabilities of events happening, not exactly with the values of the random variable. For example, if you have a big box and full of little balls, and some are blue and some are red, some are big and some are small. That's why I said blue, red, small and big here. Maybe these things are independent, but maybe they're not. Maybe the big ones tend to be blue and the small ones tend to be red. There are no numbers in here. The numbers come in the table. So how many big red balls do I have? 2. I have 3 big blue ones. I have 5 small red and 1 small blue. And then the rest of the table that you need to fill in are just the totals. So 5 big, 6 small, 7 red, and 4 blue. So that is a table of observed values, is how many balls you actually have in the box, and it's how many numbers from your data set fit into the categories that you're interested in studying. So the idea is to compare the observed values to another table that you're also going to write down of expected values. So in the table of expected values, the row totals and the column totals are the same as in the table of observed values, but then in order to fill in the table, you have to calculate how many would be there if the 2 variables were actually independent, if being big or small was independent of color in this case. And I'm going to go more into detail about how to find these numbers later in the example from the data set that I'm working with, but these are approximately correct for this example. If you remember from the other video, there was another test that was also called chi-square. That was the chi-square goodness of fit test. And maybe you see the resemblance here, because in that one we were also comparing a list of observed values with a list of expected values. So they weren't tables with two variables, but there were two of them, and we were comparing an observed one with an expected one. So that is the thing that they have in common, why they both have the same name. One difference, though, is that in that case, we had to actually type both of those sets of numbers in the calculator to compare them. And in this case, as you will see, we only need to type in the observed values because the calculator is going to do the table of expected values for us. But still, it may be important for you to know how to calculate them because you're going to have to check for a restriction that was also present in the other chi-square test, which is the fact that expected values can't be less than 5. So I made a small example here with just a few balls. There were 11 balls. And so I am coming up with smaller numbers than 5, which means that the test should not be used for this case. What we are learning here is that since the minimum degrees of freedom is 1, which means minimum 2 rows and 2 columns, 4 cells, and each cell needs at least 5 as an expected number, so the minimum number of observations that you need in order to run this test is 20. Okay, so lucky for me, I have 20 points, which is the bare minimum that I need to do the chi-square test for independence. I am just going to split this thing into 4 quadrants like this and talk about how many points I expected in each of the quadrants. But wait, it's not as simple as that. If my table of expected values is going to be 5, 5, 5, 5, then the total for my columns had better be 10, and the total for my rows had better be 10 as well. So I can't just trace this horizontal and this vertical line wherever I want, like I just did. I have to place them so that half of the points are to the left and half of the points are to the right, and also so that half of them are below the horizontal line and half of them are above. And if this is feeling a little bit like cheating, that's because it is. But that's not my fault. You're the one who's trying to run an experiment with only 20 points. I'm just trying to show you how to do it in a way that at least makes sense. So these are the lines that I'm going to use. The table of expected values is 5, 5, 5, 5. And now let's count to see our observed values. So we have only 3 here. We have 1, 2, 3 here as well. So we probably have 7 here and 7 there. Oh, that's excellent. It doesn't look random at all. So let's see how to deal with that in the TI-84. You go to Matrix, which is this tiny blue thing over here. So second, and then this button. And ignore the names, okay? There's nothing for you to do there. But over here in Edit, you're going to choose one of your matrices to put the numbers in. So let's click Enter here on the A matrix. I want it to be a 2 by 2 matrix. There you go. So now I am going to type in my observed values. It was 7337. So it looks like that. Let's get out of here. And now we are going to do stat tests. Scroll down the list until you find the chi-square test. Notice that the word independence is not written there. You just have to know that this is the one that you want. And don't get it mixed up with the chi-square golf test, which is the one that we studied in the other video. Here, I just want the chi-square test. The observed values, 7337, is what we typed in matrix A. We did not type the expected values of 5555, but that's because we don't have to. The calculator is going to do that for us. And it's going to store the answer in matrix B. So now we just calculate, and you found a P of 0.07, which is quite small, but it is still bigger than 0.05, so you don't reject the null hypothesis. And the null hypothesis was independence. So you're not rejecting independence, the same situation as you were not rejecting non-correlation either. So in other words, there is nothing that you can say at this point to save your data. And what some people do at this point is to go back and question their choice of 0.05 for a significance level. But that is a very, very questionable thing to do, because even though 0.05 is arbitrary and some people do work with 0.1 from the beginning, so if you were working with 0.1 as a significance level, you would have rejected both null hypotheses. You would have found a weak correlation and variables that are not independent. So it makes a very big difference in this example whether your significance level was 0.05 and 0.1. But it's generally not acceptable, and it's not accepted to go back and change the significance level after the fact. Because why are you doing this? You're doing this because you want to conclude something. So it's considered manipulation. You are manipulating your study to get the result that you want. That's not considered good science. Okay, so I want to do the same thing again, but now instead of 20 points, I want to do 200 points. So I'm going to put the chart here. It looks incredibly random. And with this many points, I don't think I really stand a chance of just trying again and again until I find one that suits me better. They're all very, very small. So what I want to do instead is the following. I still want to generate a big data set with 200 points that is going to be a good example for this video. So I am going to insert some correlation intentionally and then a lot of noise around that. How am I going to do that? For the A column, I'm just going to leave it completely random like it is now. And for the B column, instead of just putting rand, I am going to do cell A1 plus rand. Copy that to the other cells. Now I have something that looks like this. It's noisy, but it is correlated, right? The Pearson coefficient is 0.657, so it's kind of weak. It's bigger than 0.4 that we had the previous example, but it's still not considered very good. So let's do the t-test for correlation. That was the part that had the weird formula to calculate a t-value. So take the Pearson, multiply by the square root of the degrees of freedom, which in this case, I have 200 points instead of 20. So 200 minus 2 is 198. And then I have to divide that by the square root of 1 minus the Pearson squared. 15, that sounds like a big number, but I don't really know what the t-distribution looks like. So let's ask the probability of finding points like this under the null hypothesis that there is no correlation. So I use the tdist command with the cell C16 here as my x. The degrees of freedom is 198 and 2 tails as before. Okay, so the reason why the numbers are changing as I do this, you see that the t statistic is now 14 instead of 15. The reason why this is happening is that Google Sheets is weird. So whatever I type into whatever cell, it recalculates all the random numbers that it had generated before. But that's okay, I think, because all of them look kind of the same. All of them have similar Pearsons and similar statistics, and in all cases, the probability of finding something like this under the null hypothesis of no correlation is 0. It's obviously not 0, it's 0.0000 something, but very, very small. So we reject this null hypothesis. This kind of picture only happens when things actually are correlated, even though the correlation might not be the strongest. So one thing that I can do to make this into a more interesting example is to multiply by 2 the effect of the randomness. So now it looks more noisy, the Pearson's coefficient is smaller, the t-statistic is also smaller, but the probability of such a thing happening under no correlation is still coming out as 0. Look at this example where I multiply the randomness by 5. This is disappointing in a different way than the other disappointing things I've mentioned before. When I find a Pearson's coefficient of 0.17, it's very unlikely that I will still think that there is correlation. I will just call this random. But the probability of finding this result, if it's not correlated, is still rejecting the null hypothesis of no correlation. So it's a weird, ambiguous situation where, on one hand, you have reason to believe that your data is just random noise because that's what we're seeing and what Pearson's correlation is telling us. But on the other hand, you have this hypothesis test saying that this is not uncorrelated. Again, in this case, we know why. It's because it's not uncorrelated. I've intentionally made it correlated. But in real life, you wouldn't know that. So maybe a good time to try a different kind of test to maybe try to resolve this ambiguity. Let's try the chi-square test for independence. In this case, you have so many points that if you wanted to cross a line right down the middle here and right down the middle, you would be fine in terms of the minimum of 5 in the expected values because you would have a lot more than 5. But then I don't think that your test would have the chance to examine what is happening here. There's hardly any points here. There's hardly any points over there. So that can potentially be significant. What you want to do when possible is not to just cut it down the middle and down the middle. You have more points than that. You can cut it into more pieces. What I really want to do when I look at this picture is this. I want to cut it into 6 parts horizontally and 4 parts vertically, because then I get that empty space here and that empty space there. Okay, some sort of empty space here too. And also I'm cutting them in very round numbers like 6, 5, 4, 3, 2 here on the vertical, and 25, 50, 75, and 1 here. But now I have to make sure that I'll get everything bigger than 5 if I do it this way. So let me show you how I'm going to do that. This table is meant to represent the divisions that I just made. So less than 0.25, between 25 and 50, and so on. And here are the numbers where the B column is less than 1, less than 2, less than 3, and so on. So how do I calculate that? There is this command COUNTIF, by which I am asking him to count how many cells from B1 to B200 have a value that is less than 1. And this is slightly weird because the less than 1 needs to come in between quotations as if it was text, but that's just the way it works. And then he answers me that 12, there are 12. So in the cell right above it, I did the same thing, but asking for how many cells are less than 2 instead of less than 1. And just keeping in mind that this also includes the less than 1 that had just been counted, I am then subtracting cell G8, which was the 12 that we previously had. So in other words, for column B, we have, out of the 200 numbers, 12 of them are less than 1, 54 of them are less than 2, which means that 42 are between 1 and 2, which is exactly what I want. So for the cell right above it, I did the same thing by asking for less than 3 and then subtracting both previously counted cells. I keep doing that as I go up until in the last one I don't even use the COUNTIF command because it's just the total 200 minus everything that came before. In the vertical columns, I'm doing the same thing. So here I'm counting the ones from column A that are less than 0.25, less than 0.5, but then subtracting cell C9, which had the less than 25, and so on. Now I want to fill in this table with the expected values for each one of these 24 cells. I've done one here already as an example. So that is C9 is 55 times G3, which is 25, and then divided by 200. So what is going on here is that I'm taking the probability of the number in column A being less than 0.25, which is 55 out of 200. I am multiplying that by the probability of the corresponding number in the B column being between 5 and 6, which is 25 out of the 100. And then a probability of something times the probability of something else is what I would get if those were independent variables, because I would then just multiply the probabilities to get the probability that a selected pair was inside of that cell. But what I want is not the probability. What I want to put in the cell is the expected number of pairs that go there. So I take this probability and I multiply it by the total number of pairs that I'm going to analyze, which is 200, to get the expected amount of numbers that are going to be there. So this 200 cancels out with one of the 200s, which is why the formula that I'm using to fill in the table is number for the total of the column times the total of the row divided by 200, which is what I typed here. Now let's talk about these dollar signs that I've also typed here. For the column, I've placed a dollar before the 9 because when I take this and I copy paste it to the other cells in that column, the natural Google Sheets action would be to, well, if row 3 is using row 9, then certainly in row 4 she wants to use row 10. But I don't. I want it to stay as 9. And that is what the dollar sign does. It holds that as 9. And I don't need a dollar sign before the C, because when I copy it to this column and it's going to be D, then I do want him to change that C to a D. So that's why I did not put a dollar sign before the C. But it's different for this dollar sign here, which G3 is referring to this number. So I don't want it to change when I move sideways. So column C is using column G. Column D is also going to use column G. So I'm using the dollar sign to hold down the G. But when I move it down, row 3 is using row 3, and I do want row 4 to use row 4. So that's why there is no dollar sign before the 3 there. So I hope all of that made sense, because it's a very useful trick to know about Google Sheets, like what the dollar signs do, because now I can just Control C here and Control V to the whole table. So as you can see, the dollar signs worked perfectly. In this example, I am using E9, which is this, so E9 here, times G5, which is this. Perfect. But you do see that I got some expected values less than 5, which I have highlighted in yellow. That's not good. So let's try to fix that by changing a little bit the categories that we have used to fill in the row totals. So all 4 of these refer to this 12, which I think if I use a bigger number than 1 here, all of those numbers are going to be bigger. So for example, if my first category goes until 1.2, they have gotten bigger, and the corresponding numbers on the row above have also gotten smaller to compensate, okay? That's because over here, I hadn't explicitly said that it had to be between 1 and 2. I just said less than 2 and then subtract the previous one. So that happened automatically. When I changed the 1 to 1.2, the 12 became a 23. So I was subtracting a bigger number here. That was almost enough. Not quite for this last one here, which is still 4.485. But because I have another one in the same column that is also still having a problem, I think I'm going to change something in the columns now. So there's nothing that I can change in this one, but I can change this one. Maybe if this one doesn't quite go until 75, but stops at 7, oh, that was a little bit too much. Now I have a 4.83 here. So maybe let's try 72. Perfect. Well, not perfect. Of course, I would prefer to have categories that are all the same size, but This is just a little bit of a manipulation to make everything make sense. Now I have a table of expected values that fits all of the requirements. No expected value is smaller than 5. So now I just have to count the observed values. So in order to fill in the observed values, the commands that I'm using in Google Sheets is slightly different. It's count ifs instead of just if, because now I want to give it two restrictions. I want the first column to be less than 0.25, and at the same time, the second column to be less than 1.2, because this is the cell that I am filling in. And now I am just going to do similar things for all other 23 cells. So after doing that, this is my table of observed values. It's not as dramatic as I wanted it to be. I was hoping to get a 0 here in both corners, and I got a 2 and a 3 instead, which are small numbers, but not quite 0. And there's something else that surprised me a little, that I'm finding other small numbers in the middle of the table. This is surprising just because I hadn't been paying too much attention to that before, but it does reflect what's in the data. There's kind of some empty space here and here. It's not empty, but it's not as densely populated with points as here, for example, which corresponds to the biggest numbers that I found on my table of observed values. Anyway, unlike what happened with the t-test for correlation, I am not feeling the need to learn how to do chi-square test for independence in Google Sheets, because even though I've increased the number of points from 20 to 200, and I really don't want to type 200 numbers in the calculator, but I don't have to do that, because the information that needs to go into the calculator is just these 24 numbers. So it's not really that the amount of observations that you have is going to determine how much stuff you have to put into the calculator. It's really how many categories you chose to split your data into. So 24, that's reasonable. I'm okay with typing that. So what I need to do here again is to go into second matrix. Now I'm going to go back into edit. Let's edit matrix A again. Now I want it to have 6 rows and 4 columns. And that's it. I don't need to type the table of expected values because the calculator is just going to do that. When I go to stat, tests, choose the chi-square test. Here, again, the observed values are in A, the expected values are to be filled in B, and calculate, giving me an extremely small p-value of 5 times 10 to the negative 4. That is strong rejection of the null hypothesis of independence. This data is not independent. Not independent, also not uncorrelated like we had concluded before, but still with a very, very weak Pearson's coefficient, not to mention the absolute mess that it clearly looks like. So I think that the message here is that these things all have limitations, right? None of this is going to give you definitive, satisfactory answers about your data. It's just different aspects of your data that you analyze in traditional ways.